Two-dimensional temperature fields of variance design of a double-skin facade structure. Introduction. Today, interest in the Arctic is on the world level. This territory is a clash of economic, geopolitical and strategic interests of the leading powers of the world, which in their zeal are ready to invest in these territories. This interest is due to the broad prospect of these regions with the richest potential, including in the transport, food and energy sectors. However, many Arctic regions do not have a stable situation of the migration issue, often tending to negative migration. This problem is often associated with the low quality of the social component of such regions. The problem of social sustainability of the Arctic regions is influenced by various factors, including the natural features of the geographical location of the territories, one of which is the polar night. Its duration at the North Pole is 6 months. One such solution is the double-skin facade. It is a multi-layer construction of an outer and inner glass circuit with an air gap between them. The external circuit protects against thermal, solar, aerodynamic, acoustic and other influences, ensuring a favorable quality of the internal environment in buildings through natural ventilation, daylight, the required level of sound insulation, heat and solar energy control. The double-skin facade is the subject of this study based on the above, the purpose of which is to substantiate and prove the advantages of this design in relation to cold climatic regions and to identify the most optimal design, including the width of the buffer zone. Methods. For the study of two-dimensional temperature fields of the variant design of the structure of a double glass facade, the base region was chosen, the Arctic city of Murmansk. Murmansk is the largest city in the world beyond the Arctic Circle, which is a major maritime transport hub and fishing center of Russia, occupying a leading position in the region's economy, as well as its financial, business and cultural center. Within the framework of this study, a thermal engineering calculation of two-dimensional temperature fields was carried out according to the presented design options, Fig. 1. Today, the separation of the bearing and heat insulating functions of building materials in building structures is the basis of the concept of a heat-efficient building and increasing the level of its thermal protection. 9, 10. The normalized value of the reduced resistance to heat transfer of the enclosing structure, R_0 norm, M2*C, W, should be determined by the formula. Within the framework of these studies, the main goal was to justify the use of a double facade design with the identification of the most optimal width of the buffer zone, taking into account the fulfillment of the sanitary and hygienic requirements, Clause 5.7 of Russian Code of Rules, SP 50.13330.2020, which regulates that the surface temperature should be higher than the dew point under design conditions. The studies were carried out by calculating the temperature fields of structures. All calculations to reduce the number of nodes are logically fragmented along the axis of symmetry. The Elcut 6.4 software was used for calculations. 2.1.HEAT Engineering calculation of option 1. Gas silicate masonry, 400 mm. Figure 2 shows the result of heat engineering calculation of option 1. Gas silicate masonry with the image of isolines and heat flow. These temperature fields, Fig. 2, 3, correspond to the following numerical results, Table 1. In this table and the following designations are used. F. Heat flux over two internal surfaces, W. Increment T temperature difference between two internal surfaces, OC. Ts. Average temperature two internal surfaces, OC. Tf. Surface temperature in the corner between the floor and the wall, OC. Table 1. Calculation results for option 1. Gas silicate masonry, 400 mm. 2.2 Thermal engineering calculation 2 options. Double facade, buffer zone width 200 mm. Figure 4 shows the result of the heat engineering calculation of 2 options. A double facade. The width of the buffer zone is 200 mm. Table 2. Calculation results for option 2. Double facade, buffer zone width 200 mm. 2.3 Heat engineering calculation 3 options. Double facade, buffer zone width 400 mm. Figure 6 shows the result of the heat engineering calculation of 3 options. Double facade. The width of the buffer zone is 400 mm. Table 3. Calculation results for option 3. Double facade, buffer zone width 400 mm. 2.4 Heat engineering calculation 4 options. Double facade, buffer zone width 600 mm. Figure 8 shows the result of the heat engineering calculation of 4 options, a double facade. The width of the buffer zone is 600 mm. Table 4. Calculation results for option 4. Double facade, buffer zone width 600 mm. 2.5 Heat engineering calculation of the 5th option. Double facade, buffer zone width 800 mm. Figure 10 shows the result of the heat engineering calculation of the 5th option, a double facade. The width of the buffer zone is 800 mm. Table 5. Calculation results for option 5. Double facade, buffer zone width 800 mm. 2.6 Heat engineering calculation of the 6th option, double facade, buffer zone width 1000 mm. Figure 12 shows the result of the heat engineering calculation of the 6th option, double facade. The width of the buffer zone is 1000 mm. Table 6. Calculation results for option 6. Double facade, buffer zone width 1000 mm. Results and decision. The results of the study of two-dimensional temperature fields of the variant design of the structure of a double glass facade, in particular 6 variants, are summarized in Table 7 and Figure 14. Table 7. Summary of the results of 6 options. From the data obtained, it can be observed that with an increase in the buffer zone from 200 mm to 1000 mm, the average temperature of the two inner surfaces, Ts, increases systemically. Accordingly, with an increase in the width of the buffer zone, the temperature difference between the two inner surfaces, increment T, decreases. The most optimal widths for the buffer zone can be taken as 200 mm and 600 mm if it is necessary to provide a passage in the buffer zone. For the variant with a technical passage, a cantilever base for the passage should be provided. In addition, ventilation openings in it should be designed. Conclusions. 1. The use of a double facade structure in a cold region is justified. The fulfillment of the sanitary and hygienic requirements, Clause 5.7 of Russian Code of Rules, SP 50.13330.2020, is taken into account, which regulates that the surface temperature must be above the dew point under design conditions. 2. With an increase in the buffer zone, the average temperature of the two inner surfaces increases systemically, and, accordingly, the difference in their temperatures decreases. 3. The most optimal widths for the double-skin facade buffer zone in Murmansk can be assumed to be 200 mm and 600 mm if it is necessary to provide a passage in the buffer zone. For the variant with a technical passage, a cantilever base for the passage should be used. In addition, design ventilation openings in it. 4. The glass channel as part of the double-skin facade offers a stunning alternative to traditional opaque building walls and flat architectural glass, creating virtually seamless facade surfaces. 5. The use of the double-skin facade for architectural solutions in cold climatic regions is justified not only as a self-illuminated effect, but also demonstrates sufficient energy efficiency due to the selection of the optimal width of the buffer zone. Thank you for the attention.